Hello viewers, welcome to today's lecture on routing. In fact, this is the first lecture on routing in switched communication network. Here is the outline of today's talk. First, we shall discuss about what is routing. In other words, we shall define routing. Then we shall consider various properties, desirable properties of routing. And as we shall see, we have to develop routing algorithms. And so, whenever you develop routing algorithms, what are the design parameters? We shall consider in detail. Then we shall consider about discuss about two routing algorithms. One is known as fixed routing, and in this context, we have to discuss some algorithms on shortest path. For finding out the shortest path, we shall discuss Dijkstra's shortest path algorithm. Then we shall discuss another routing algorithm known as flooding. So, we shall primarily discuss two important routing techniques, fixed routing and flooding, in this lecture, and in the next lecture we shall discuss some more routing algorithms. And on completion of this lecture, the students will be able to understand the need for routing. They will understand what is routing, and they will understand the desirable properties of routing. Then understand various routing algorithms such as fixed routing, flooding, and also, as I mentioned, the students will be able to understand the shortest path algorithm, and they will be able to find out a shortest path from a particular source to a destination in a switched communication network based on this algorithm. So, first let us focus on what is routing and why it is needed. Here a typical schematic diagram of a switched communication network is given. Here, as you know, we have a number of stations, A, B, etc., and a number of nodes. Nodes are essentially switches, and as we know, the stations are connected to nodes, and nodes in turn may be connected to some other node or connected to other stations. And as we can see, suppose station A wants to send packet to, say, station D. In such a case, as you can see from this particular network or switched communication network, that there is no direct path, or in other words, A is not directly connected to the station D, or in other words, both of them are not connected to the same node. So, as you can see from A, it can go via several nodes. Say it can go via a node 1, then to node 2, then to node 6. In this way, the packet from station A can go to station D. As we find from this, this is not the only route or path. There exist several alternatives. For example, it can go via 1, then to 3, then to 5, then to 6, or it can go via 1, then to 4, then to 6. So, we find there are several alternative routes. Question arises, which route is the optimal? And at a particular instant, a particular route may be efficient. In other words, it will be better to send through a particular route, and maybe at the next moment, because of node failure, because of congestion, that particular route may not be possible. So, we may have to send through alternative route. So, the key point that I would like to make is, from a particular station to another station, source to destination, there exist multiple paths, and routing is a mechanism for finding out the most cost effective path from a source to a destination. So, for a source destination power, the intermediate nodes through which the packets are to be routed is given by the routing algorithm. And as a consequence, routing is one of the most complex and crucial aspect of packet switch network design. So, whenever somebody is designing a packet switch network, the routing, the way the routing has to be done plays a key role or important role in the design. That is why we shall devote 2 lectures on this routing. Now, let us see what are the desirable properties of routing. We want the routing algorithm to deliver a packet from a source to a destination. Now, first 2 important properties are correctness and simplicity. These 2 terms are self-explanatory. By that I mean, whenever we say correctness, that means the packet should be delivered to the correct destination. If source is A and destination is D, it has to be delivered to the proper destination station. So, that is what is meant by correctness. By simplicity we mean the routing algorithm can be simple, can be very complex depending on which one we are using. Now, if it is complex, then it will put large overhead on the nodes. So, it is necessary to make the routing algorithm simple. So, these 2 terms are quite simple and easy to understand or self-explanatory, correctness and simplicity. Then comes the second important property, that is robustness. As you will see, the network is a queue of packets. The queue sizes keep on changing dynamically with time, and also there will be there is a possibility of some node failures. So, under the situation of node failure, under the situation of congestion in some part of the network, the routing algorithm should be robust, so that it can deliver packets via some route even in the face of failures. So, even in the face of failures, even in the face of congestion, it is necessary that routing algorithm is able to deliver packets to the proper or to the correct destination. That is what is meant by robustness. So, this property is very important whenever the network load is changing dynamically, failure is also taking place occasionally or frequently depending on the network. Third important property or fourth important property after correctness, simplicity, robustness is stability. The algorithm should converge to equilibrium first in the face of changing condition in the network. As I mentioned, the queue of packets may keep on changing quickly in the network. So, in such a situation, suppose there is congestion in this part of the network, then what can happen, a particular station can divert all the packets in towards another nodes, or not one station, all the stations can divert all the packets to another part of the network. When what can happen, because of that the congestion may develop in that part of the network. Again, those packets are diverted to previous node, previous part of the network where there was congestion. So, in this way what can happen, because of quick routing of the packets or changing the routes from one congested area to another congested area, what can happen, it cannot reach stability, and as a result it may lead to unnecessary delay in delivering the packets. So, that is why it is important that the algorithm should converge to equilibrium first in the face of changing condition of the network. So, even when the loads are changing, even when there is some failure, the routing algorithm should be stable and should converge to equilibrium quickly. This is the important property of the routing algorithm. Finally comes the fairness and optimality. What is desired is each and every station should have equal right for getting a particular route for delivering their packets. But because of optimal routing, it may be necessary that some packets from a particular station is given some priority. So, if you give priority, then fairness is violated. On the other hand, if you give priority to some nodes or to a particular path, for example, if you give priority to packets which are to be delivered to adjacent nodes, then the nodes of the long distance nodes do not get the fairness. So, these two terms are little conflicting. So, you have to, these two are important. So, you have to arrive at some trade off between these two, fairness and optimality, and obviously although they are conflicting, you can arrive at some trade off and find out some mechanism of giving some kind of weightage or priority without violating the fairness or without compromising much of fairness. Then finally, the efficiency. As I mentioned, the overhead of routing should be as little as possible, but if the routing algorithm is very complex, then it will put very high overhead on the nodes in the network. That is why the routing algorithm should be simple, and so that the overhead of efficiency of the routing is high, and the packets are delivered in a efficient manner through the shortest path routes or at a low cost. Okay. Now let us focus on the design parameters. So whenever you try to design a routing algorithm, you have to consider several parameters, take into consideration several parameters into account. First is the performance criteria. What performance criteria you will use in designing in finding out the efficacy or effectiveness of a particular routing algorithm? One cost parameter, performance parameter, is number of hops. As you have seen, whenever packets are going in a network, it is making several hops. So, how many hops it makes through the intermediate nodes, that count can be a measure of the performance. Another parameter can be cost. Suppose you have got a node and you have got several paths. Now, you have got several alternatives. Now, the bandwidth of these particular links may be different. Now, if the bandwidth is high, then the average cost for sending through that particular path may be smaller. So, it may be desired, you may consider that you will try to send the packets through a high bandwidth route, so that the cost is less. So, the cost is inversely proportional to the bandwidth of a particular link. Then comes the third important performance criteria, that is delay. Delay is usually dependent on the size of the queue. So, in a particular route, if there is a long queue of packets, then delay will be longer. So, that delay can be measured as a performance criteria, and a measure of delay can be obtained from the size of the queue or queue length. Then fourth important criteria is the throughput. Throughput is essentially the number of packets delivered per unit time. So, that number of packets delivered per unit time can be found out, and which can be used for measuring the effectiveness of a particular routing algorithm. So, these are the various performance criteria that can be used in designing a routing algorithm. Second question or second important parameter is the decision time. Now, decision time means when you will decide for routing a packet. The decision can be per packet basis. For each of the packets, each of the node will decide, for each of the packet it is independently decided what should be the route for that particular packet. On the other hand, it can be per session basis. For example, in virtual circuit network, as you know, for a particular session a virtual circuit is established and all the packets for that session or during that session are sent through the same route or path. So, decision time is important whether it is per packet basis or per session basis, and accordingly you have to use a datagram type packet switching or you have to use virtual circuit packet switching. Then the third important parameter is decision place. Who will decide about routing? Where it will be decided about routing? For example, whether it will be decided in each node. That means each node receives a packet, then it decides the route for that particular path, to which particular output link it has to be forwarded. So, in that case we call it distributed. Another possibility is that there can be a central node or central control node. So, in that central control node we will have some kind of routing table and which will decide about routing. Then we call it centralized. Or it can be decided by the originating node, the node where it is originated. So, that decides where it has to be, in which direction it will go or what will be the next node. So, the decision place can be each node, central node or the originating node. In that case we call it source routing. So, this is the third important design parameter. Fourth important design parameter is network information source. Now, you will see there exist algorithms for routing which does not make use of any information, neither the topology nor the offered load nor the cost in different paths. So, it does not use anything. So, in that case we call it none. In the second case, it may use some local information. For example, you have got a node and you have got say 3 links. So, the output queues, the queue length of each of these in each of these paths may be considered as the information that is being used for routing. So, in that case we call it local. It does not gather information from its neighbors or any other node. The third possible alternative is that a particular node gathers information from the adjacent nodes, from its neighbors, and accordingly does the routing. Then we call it adjacent node. It gathers information from adjacent node, or it may be nodes along the route. The particular node before routing gathers information from all the nodes along the route, then decides whether it will forward in that route or in some other nodes. Or it can be very global. In such a case, each node gathers information from all other nodes at regular interval, and accordingly it makes some kind of routing table, as we shall see, to decide about routing. So that network information source can vary from none to all nodes. So, and depending on that, obviously the complexity also will vary. Finally, the network information update time. That network information update time can be continuous. First, in the first place, as I told, the routing algorithm should decide whether it will use what kind of information, local or from neighbors or none or global. So, whenever it is local, it can be continuous, or if it is from the neighbors or if it is from all other nodes, then it can be periodic. Or it can be that whenever some major load change is taking place, only then it makes change in the routing algorithm. So, whenever there is a major load change or topology change, there is a change in the network topology, then only the network updates information and changes the routes accordingly. So, you see that these are the various design parameters which should be used in developing routing algorithms. So, a large number of routing strategies have been evolved over the years, and some of the important strategies are fixed routing, flooding, random routing, flow based routing, adaptive or dynamic routing, and so on. So, in this lecture I shall discuss about two important routing algorithms, the fixed routing and flooding, and other algorithms we shall discuss in the next lecture. So, first let us focus on fixed routing. In fixed routing, a route is selected from each source destination pair of the nodes in the network. The routes are fixed. They may only change if there is change in the topology of the network. That means for a given topology of the network, the routing is fixed. So, it changes only when there is a change in the topology of the network, otherwise it remains the same. And question arises, how fixed routing may be implemented? There are several alternatives. Let us see how it can be done. Here, as you can see, there is a central routing matrix is created based on least cost path, which is stored at a network control center. Now, there is a network control center where this central routing directory is created based on the and here what is being stored, as you can see, it stores the so suppose this is the from node 1, from node 1 you have to send a packet to node 6, then what will be the next node, or in which node it has to be forwarded. For example, from 1 it has to be, if it is going to be 6, then next node to be forwarded is 2, and cost of each link is given here. This cost may be maybe the queue length, based on queue length, or it may be based on the bandwidth of the network. Whatever it may be, some cost is assigned, and these cost for each of these links are given here. Here the links are bidirectional, and that's why we can say this is a weighted graph. That means all the edges has some weight, and these weights are essentially assigned as the cost of a particular link. Now here you can see, say from any node to any node, what is the next node to which a particular packet has to be forwarded is given here. For example, if the destination is say 3, then from 1 it has to be forwarded to directly to 3 because it is directly connected. On the other hand, if it is 4, then it has to be forwarded to 2, then it will go it will be forwarded to 2, then after that where it will go, that can be obtained as we shall see later. So, in this way, such a big routing directory has to be stored in the network control center. This particular approach, this centralized control, has one drawback. The drawback is if this network control center fails, then everything will collapse. That means the routing cannot be done. As a consequence, it is prone to failure. That means it is not very reliable. So, it is not a very reliable approach. Another alternative is to divide this routing directory and create separate directories for each of these nodes. That means in each node you can keep a small copy of this particular directory. Previously we have seen there is a big directory, and from this you can create directory corresponding to each of these nodes. Essentially, for a given destination, what will be the next node to which it has to be forwarded, that is being stored in this directory. That means if the destination is 2, next node to be forwarded is 2. If the destination is 3, then the next node to be forwarded is to 3. So, this is the directory for node 1. If the next node is 5, it has to be forwarded to 2. As you can see, for 4, 5 and 6, if these are the destination nodes, the packets are to be forwarded to node 2 for all the cases. This is quite evident from this topology. So 4, 5, 6, as you can see, from 1 it will go to 2 for delivering to 3 packets. So in this way, in this case, from the main routing matrix, routing tables are used by each individual node. These routing tables can be developed and which can be kept in each of these nodes. So this is a distributed routing algorithm. So here, as you can see, these tables, each of these tables can be kept in each of these nodes, and as a packet is received for a particular destination, it is forwarded to the next nodes. In this way, the routing can be done based on the information of next node available in the routing directory. So these are the routing directories to be kept. Question arises how these routing directories will be created, and that can be created based on some cost. It can be least cost path. As I mentioned, a cost is associated with each link, as we have seen. Now the simplest criterion is to choose the minimum hop path route through the network, and this minimum hop route, that means you can find out how many hops the packet will take. Based on that, a routing table is created. However, the generalization of this is least cost routing. As I mentioned, this least cost can be based on several parameters, like it can be based on the load, that means queue length at different parts of the network. It can be based on the bandwidth at different nodes or distance of different links. So whatever it may be, the least cost can be associated with each link, and accordingly the corresponding least cost path can be created. So for any pair of attached stations, the least cost route through the network is looked for. Question arises, how do you find out this least cost route? And for this, several well-known algorithms have been developed to obtain the optimal path. These two algorithms are very popular, Dijkstra's algorithm and Bellman-Ford algorithm. These two algorithms are quite similar and performance is also similar. What they do, for a given topology and for a given cost associated to each of these links, a least cost path is found out from a particular source to all the destinations. That is being done with the help of this least cost routing algorithm, or rather the Dijkstra's algorithm for obtaining optimal path. Let us see how it is done. It finds the shortest paths from a given source node to all other nodes in order of increasing path length. The algorithm converges under static conditions of topology and link cost. That means when the topology is fixed and link cost associated with each link is given, then it will find out, it will converge to a solution, and it will give you the optimal paths. And it has got 3 steps. Initialization, first it creates an initial set starting with the source node, and also a cost dn, which is essentially the distance that based on the link cost from source node to a particular node, and when n is not equal to s for all nodes for which n is not the source node. And find neighboring nodes not in M that has least cost path from S to S and include it in. So in this way, in an iterative manner, it will find out the it will choose a particular node and include in M and update the least cost paths. So let me illustrate this with the help of an example. So here, as you can see, we have got a network, and the topology is fixed, the interconnection is fixed, then the cost associated to different links are given here in this network. Now in first iteration, as I told, in first iteration M is the source node. So here the source node is 1, and as you can see this node is connected to node 2, node 3. So the cost for this path from 1 to 2 is 2, as you can see it is 2. Then cost from 1 to 3 is also 2. So 1 to 3 is 2, and since from 1 we don't know the cost for 4, 5 and 6 right now, the cost is not known. So these are given as infinity. So there is no path to 4, 5 and 6, and cost is given infinity in the beginning. So this is after the first iteration. Then after second iteration, this 2 is included as part of M, because this is the least cost path among the available paths. So after including 2, you can see now you can get a path to 4 as well as 6. So for 4, the path is now through 1, 2 and 4. So cost is 6. So 2 plus 4. So these are the link costs. These are added and you get a cost 6. And for 5 is not yet linked to, I mean there is no path from 1 to 5 through 1 or 2. So for 6, as you can see, the path is 1, 2 and 6. So cost is 2 plus 1, 3, as it is given here. Now in the third iteration, 3 is added in the list, and after adding 3, obviously the 5 is also now reachable from 1. And after including 3, now we find the cost for 2 from 1 to 2 remains the same, cost from 1 to 3 remains the same, but cost for 4 has now changed, because now there is a path after including 3, as you can see, after including 6, because 6 has been already included here. So now there is a path 1, 2, 6 and 1, 2, 6 and 4. So now there is a path 5, cost is 5, and here to 7, to 5, the cost is now 7 through the path 1, 2, 6, 4 and 5. So cost is now 7. Now 6 is added to the list, and after adding 6, we find the cost is 1, 2, 3 and 6. Cost is now, it remains unchanged for this, and after adding 6, now it is actually in the previous case it should have remained 1 to 4. Here is a mistake. Here it should become 5. Cost should become 5 with 1, 2, 6 and 4 after including 6. So now cost is reduced from 6 to 4 through a longer path. So the number of hops is increasing, as you can see from this, but cost is decreasing. And for 5, the cost remains same, 1, 2, 6, 4, 5. So cost is 7. Now here after this cost also remains same, 1 to 6. Now you have to include this 4 into this set, and after including 4, now the list is 1, 2, 3, 4, 6, and this cost remains unchanged. Here also it remains unchanged. 1, 2, 6, 4, 5, it remains unchanged. Here it becomes 1 to 6. Now we find the final solution and everything remains unchanged. So we find that from 6 to from node 1, after 6th iteration we get paths to all the remaining nodes. For 2 it is 1 to 2, cost is 2. For 3 it is 1 to 3, because direct link is there, cost is 2. For 4 the cost is 5, and through the path 1, 2, 6, 4. So when we create the table, so you have to forward it to 2 from 1 to 2 to forward for a packet to with destination address 5. Similarly for node 5 the cost is 7, and again it has to be forwarded to 2, but it will make several hops, 1 to 2, 2 to 6, 6 to 4, then ultimately it will go to node 5. Similarly for delivering packet to 6, the path is 1, 2, 6 and cost is 3. So from this you can create that table, routing table, which I mentioned earlier, whether it is a central routing table or distributed routing table, that can be created from these least cost path algorithm given by Dijkstra, and it is quite efficient algorithm, and that is why it is widely used. Now, what are the advantages and disadvantages of fixed routing? As you have seen, fixed routing is simple. Simple in the sense, for a given topology and the cost is given, and after the least cost paths are obtained using the Dijkstra's algorithm or Bellman-Ford algorithm, you can use it, and it is quite simple after the routing table is created, and it works well in a reliable network with stable load. I think it has become twice. It works well in a reliable network with stable node. This is not necessary. And another important feature is whether it is virtual circuit or it is datagram type of packet switching, this approach, this fixed routing algorithm is same. It does not change, because route is decided based on a routing table created based on those least cost routing algorithm. And it has got several disadvantages. First disadvantage is that there is lack of flexibility. Lack of flexibility arises because, as we know, a network is dynamic in nature. It cannot take care of that changing situations, changing load conditions, because routes are fixed. As long as topology does not change, the route does not change. So it does not react to failure or network congestion. So these are the limitation of this fixed routing algorithm, and that is why fixed routing algorithm is not very suitable whenever we are working in real life. In real life, we have to take care of the dynamic conditions, and we have to use those adaptive algorithms, as we shall discuss in the next lecture. However, this fixed routing is used in some situations where the network is reliable and load is stable. Next comes the flooding algorithm. This flooding algorithm has a very unique property. It does not require any network information, neither the topology nor the load condition nor the cost of different paths. It does not require anything. What it does, every incoming packet to a node is sent out on every outgoing line except the one it arrived on. So it simply forwards in all the path except through which it has come. Let us see how it happens. So let us assume a packet from A has to be delivered to some destination, maybe D or maybe C. How it works, let us see. So from A it is sent in through both the links. So in the first after that, so the packet has been received by 2 and 3 through these links. Now what 2 will do, it will forward through these 2 links, and 3 will also forward through these 2 links. So as you can see here. Now 4 has received, 5 has received, and 6 has received. These 3 nodes have received packets. So they will again forward in all directions. So as you can see, to deliver a single packet, a large number of packets are generated. This is the very alarming situation. So we find that this technique has some important characteristics. All possible routes between source and destination are tried. A packet will always get through if a path exists. The flooding algorithm has some important characteristics. First important characteristic is that all possible routes from source to destination are tried, because the packet is visiting all the destination, all the nodes, and it explores all the nodes, and as a result if there is a path it will always get through if a path exists. That means it is very robust under any condition, failure, congestion, a packet will be delivered, it is guaranteed. So that is why it is very robust and reliable. As all routes are tried, at least one packet will pass through the shortest route. Not only it will deliver packet to the destination, possibly multiple packets will be delivered and one will be delivered through the shortest path. So first packet that it will receive is through the shortest path with minimum delay. So this is another important feature. So when somebody is trying to find out the least cost path, it can be used also from a source to a destination in a dynamic condition. The third important feature is all nodes directly or indirectly connected are visited, as I mentioned. So because of these important characteristics, this routing flooding algorithm is very useful. However, it has got several disadvantages. The limitations are flooding generates vast number of duplicate packets. As we have seen, to deliver a single packet, many multiple copies are being made, and if it is not contained, the number of such duplicates will increase alarmingly. Number increases in an unbounded manner. So suitable damping mechanisms must be used. So if we use flooding, then the network will receive a large number of packets which may make it congested. We do not want that. So to overcome that, what has to be done? We have to take some measure such that the number of packets does not increase in a unbounded manner. It does not increase alarmingly. How it can be done? One important technique that is being used is known as hop count. Hop count is a technique that is used in some situation. A counter is used, it is contained in the packet header, which is decremented at each hop. That means the header has got a count, and it is initialized with some value. You may be asking, what you should set with what value? You can set some number, but if no number is known, then usually the full diameter of the subnet, that can be used. Essentially it is the worst case value. So if no other value is known and the counter is set with some worst case value, then after each hop that count value is decremented by 1, and whenever it becomes 0, that particular packet is discarded. It is no longer forwarded, and as a result the number of packets will not increase alarmingly. So this is very important feature, and this hop count helps us to minimize the number of packets under flooding condition. Another technique that can be used is it keeps track of packets which are responsible for flooding using a sequence number. That means the sequence number keeps track of which packet is flooding the network. So whenever it comes second time, it is not forwarded. So avoid sending that packet second time whenever it comes to a node. First time it is forwarded, that sequence number information is monitored, and whenever it comes again, it is not forwarded. So this is another important technique that can be used to reduce the number of packets in the whenever you are using flooding. Now another approach which is some modification of flooding is known as selective flooding. It is a variation of flooding technique which is known as selective flooding. What it does, the routes do not send every incoming packet out on every line, only on those lines that go in approximately in the direction of the destination. In the example that we have discussed, there we have seen a packet is forwarded in all direction except through which it has received the packet. Now, it may be forwarded in the direction in the opposite direction of the destination. That is being restricted in the selected flooding technique. There it is known in which direction the destination exists. Some weightage can be given for forwarding a packet in a particular direction. So, that weightage can be used to decide whether it is going towards the destination or in the opposite direction of the destination. Later on in the next lecture we shall discuss about it in more details. So, this selective flooding also restricts the number of packets in the network. So, we find that the flooding has some important properties, some limitations, but it has some important utilities because of the advantages. First of all, flooding is highly robust and could be used to send emergency messages. For example, whenever there is a war, there is a possibility that some of the nodes will be destroyed by the enemy, some link may be destroyed, or the network topology keeps on rapidly changing, the load keeps on rapidly changing, but some emergency message has to be sent to a particular destination. Under such case, a flooding technique can be used, and so it is in military application it is very useful. Then it can be used to initially set up the route in the virtual circuit. As we know, in the virtual circuit initially a route is set up. Question arises how it will set up. It can take help of the flooding algorithm to find out the best possible route. So, by flooding the whenever the destination node receives the packet, the first packet with minimum delay, it sends an acknowledgement with information about the routes through which the packet has gone, and that can be used to set up the virtual circuit. Then subsequently all other packets can be sent through the same route. And as I already mentioned, flooding always chooses the shortest path since it explores every possible path in parallel. So, this is another important advantage, and that is why it is useful. Can be useful for decimation of important information to all nodes. So, there are some situations where you have to broadcast a particular message. Now, all the fixed routing algorithms that you have seen, where it is essentially from a source to a destination, it is not for multicasting, it is not for broadcasting, but flooding can be used for broadcasting. Suppose you have to upgrade some network, some configuration, or pass on some information to all the nodes in the network. In such a case, flooding can be used. So, we find that in spite of the disadvantages of flooding, because it increases the load in the network, it has many utilities because of its robustness and other advantages. So, we have discussed in this lecture the why routing is important, what are the important features that is desired from routing, what are the parameters that is used in routing. We have also discussed two important routing techniques, that is fixed routing and the flooding. Now, let us consider some review questions. First question is, why routing is important in a packet switch network? Second question is, what are the primary conditions that affect routing? Third question is, what is flooding? Why flooding technique is not commonly used for routing? in what situation flooding is most appropriate, how the drawbacks of flooding can be minimized. So, these questions will be answered in the next lecture. Now, it is time to give the answers to the questions of lecture number 19, the previous lecture. First question was how the drawback of circuit switching is overcome in message switching. Answer is message switching is based on store and forward technique. Instead of establishing a dedicated path, the message is sent to the nearest directly connected node. Each node stores the message, checks for error and forwards it. It allows more devices to share the network bandwidth, and one message can be sent to several users. Destination host need not be on the same time and need not be on at the same time of sending the message. So, we find that in case of circuit switching, like telephone network, which you use in telephone network, unless the destination telephone number is free and the person who will be receiving the message is awake or available in the house, you cannot set up a link and talk over the telephone. On the other hand, if you want to send, say, email, if somebody is sleeping at that moment, you can send the email. So, that is the difference between the circuit switching and message switching. So, message switching first of all does not make full utilization of the bandwidth, and a dedicated path has to be set up before sending any message, which is not necessary in message switching, which is based on store and forward, even when the destination node is not on or the person who is using that particular node is not awake. Even then the packets can be forwarded in message switching and it will be delivered. So, that is how the drawback of circuit switching is overcome in message switching. Then the second question was what is the drawback of message switching, how it is overcome in packet switching. In message switching, the large storage space is required at each node to buffer complete message blocks. On the other hand, in packet switching, messages are divided into subset of equal length, which are generated in the source node and reassembled to get back the initial complete message in the destination node. Moreover, to transmit a message of large size, link is kept busy for a long time, leading to increase in delay for other messages. As we have discussed in the last lecture, message switching has got a number of drawbacks. First of all, it monopolizes the storage. I mean, it blocks large storage area because messages are of large size. Moreover, whenever it is sent, it takes very long time, and as a result, it monopolizes the link, and also the possibility of error increases because the length of the message is long. On the other hand, whenever you are doing packet switching, messages are divided into shorter, smaller sizes, and as a consequence, possibly it does not require larger storage, it does not monopolize a link, and also possibility of error while transmission reduces because packets are of smaller sizes. Third question was what are the key differences between datagram and virtual circuit packet switching. One point that I would like to make is both datagram and virtual circuit packet switching are based on store and forward approach. However, there is a difference between the two. In datagram, the packets are routed independently and it might follow different routes to reach the destination in different order. That means each packet is treated independently. So, what can happen, like as it happens in a postal system, the different packets may go through different route and may be delivered out of order. On the other hand, in virtual circuit packet switching, first a virtual connection is being established, maybe by flooding as I have discussed, and all the packets are sent serially through the same path. In this case, packets are received in order. So in virtual circuit packet switching, it is also store and forward approach. Only difference is that it is sent through the same route, same path. As a result, the packets are delivered in order. Fourth question was, distinguish between circuit switching and virtual circuit packet switching. Answer is, in circuit switching a dedicated path is established, data transmission is fast and interactive, nodes need not have storage facility. However, there is a call setup delay. In overload condition, it may block the call setup. It has fixed bandwidth from source to destination and no overhead after the call setup. So there is no extra overhead except the propagation time. In virtual circuit packet switching, there is no dedicated path. It requires storage facility and involves packet transmission delay. Because you are storing it, then forwarding it, there is a packet transmission delay. It can use different speed of transmission and encoding techniques at different segments of the route, which cannot be done in circuit switching. The last question was, how packet size affects the transmission time in a packet switching network. As I mentioned, initially transmission time decreases as packet size is reduced, but as packet size is reduced and the payload part of the packet becomes comparable to the control part, the transmission time increases. That means if header size becomes comparable to the payload size, then the transmission time increases. This I have discussed in detail in the last lecture. So friends, with this we come to the end of today's lecture. Thank you.